Welcome to another in the series of demonstrations designed to get you quickly up to speed with what's new in NX-CAM. This video will demonstrate how you can simulate robotics machining using NX-generated milling toolpaths. Robotic machines are useful for milling, polishing, lynching, deburring, and laser, plasma, and water jet cutting. In this example, we'll polish both sides of a turbine blade. Note that you will need to have the appropriate license to simulate robotics. We'll begin by looking at the milling tool used to create the tool path and the polishing tool that will be used in the robotic simulation. Replay the tool path of the variable streamline milling operation. Click Verify Tool Path. The milling tool used to create the tool path is displayed. Select Assembly from the tool list to see the polishing tool the robotic simulation will use. Click Play. The robotic machine will use the head and polishing tool defined in the machine tool view. Next, we'll select a robotic machine tool from the machine tool library. Double-click Generic Machine. Click Retrieve Machine from Library. Select Robot from the Class to Search list. Click OK. Select the 6-axis robot from the Machining Items list. Click OK. Select Use Part Mount Junction from the Positioning list. Select the center point on the face of the mounting bracket. Click OK in the Part Mounting dialog box. Click OK in the 6-axis robot dialog box. Close the information window. You can also display the entire robotics workstation. Display the assembly navigator. Select the Polishing Station checkbox to display the station. Select the Polishing Station checkbox again to remove the station display. Next, we'll simulate the robotic machine tool and observe the movements that need to be changed. Display the Operation Navigator. Click the operation. Click Simulate Machine. Be sure the Show Tool Path and Show Tool Trace checkboxes have been selected. Click Play. Notice the excessive head rotation as the tool changes direction along the zigzag tool path. We will eventually correct this by editing the robotic machining rules to control the head orientation. Now we'll examine the kinematics chain and use preview motion to observe the robotic arm movement and rotational limits. Display the machine tool navigator. Clicking the objects will highlight the various components of the machine tool. Right-click and select Preview Motion. Click Show Machine Axis Positions. You can use the sliders to manually control each joint of the robotic arm and observe the rotational limits. The blue dot for J5 indicates a singularity or excessive joint rotation of J4 and J6 caused by J5 approaching its allowable 120-degree limit. We'll correct this singularity by editing the robotic machining rules to control the joint rotation. In the Preview Motion dialog box, select Move Spindle About Part. This allows you to observe the robotic arm movement by dragging the graphic handles. Next, we'll specify the blade and clamps as the part component in the kinematics chain. This will allow us to check for collisions between the robotic arm and the part and fixture. In the Machine Tool Navigator, double-click Part to edit the object. Select the blade and fixture bodies to define the part component. These fixture bodies are the ones most likely to collide with the arm. Click OK. We'll now eliminate the collision by editing the robotic machining rule that controls the head orientation. The Edit Rules and Apply Rules icons are new and unique to robotic simulation. With the operation still selected in the Operation Navigator, click Edit Rules. In the Events Used section of the dialog box, double-click Robot Tool Orientation, Orientation Mode equals Tangent to edit the event. Select Fixed from the Orientation Mode list. Select Inferred Vector from the Fixed Tool Direction list. Select the top edge of the clamp to define the fixed orientation of the head. This orientation will prevent the arm from swinging too far to the left and right so it avoids colliding with the fixture. Click OK in the Robot Tool Orientation dialog box. Click OK in the User Defined Events dialog box. Click Apply Rules. Now we'll simulate the machine tool movement. Click Simulate Machine. Click Play. The excessive left-right head rotation has been eliminated and the head no longer collides with the fixture, but the J5 singularity still needs to be corrected. Click Continue until reset. Click Close. One way to resolve the J5 singularity in this case is to edit the Positioner rule. Click Edit Rules. In the Events Used section of the dialog box, double-click Positioner Mode equals Constant Joint Value to edit the event. Select Constant Surface Normal from the Positioner Mode list. Select the ZC vector from the Target Normal Direction list. This will cause the head to remain vertical. Click OK in the Positioner dialog box. Click OK in the User Defined Events dialog box. Click Apply Rules. Click Simulate Machine. Click Play. The positioner tilts the blade, allowing the head to remain vertical as specified. Collisions and singularities have been removed. Click Close. We'll complete the simulation by specifying non-cutting moves that will allow us to safely rotate the blade and polish the opposite side. For robotics, it is essential that we specify a linear motion output type because circular moves, spline motions, and drill cycles are not currently handled. Once this has been done, we'll be able to copy and edit the operation to polish the opposite side of the blade. Double-click to edit the operation. Select non-cutting moves. Select the Engage tab. In the initial section of the dialog box, select Arc Normal to Part from the Engage type list. Select the Retract tab. In the final section of the dialog box, select Same as Initial Engage from the Retract type list. Select the Transfer Rapid tab. In the initial and final section of the dialog box, select Along Tool Axis from the Approach Method list. Type an appropriate approach distance value. Select Along Tool Axis from the Departure Method list. Type an appropriate departure distance value. Click OK. In the Machine Control section of the dialog box, select Line from the Motion Output type list. Click Generate. Click Overwrite Path. Click OK to complete the operation. It is important to note that you must always apply rules after generating a toolpath. Click Apply Rules. Click OK. Now we'll copy and edit the existing operation to polish the opposite side of the blade. We'll also edit the robotic machining rule to specify an appropriate head orientation. In the Program Order view of the Operation Navigator, right-click the operation and select Copy. Paste the operation inside the program. Double-click to edit the copied operation. In the Drive Method section of the dialog box, click Edit. In the Materials Side section of the dialog box, click Flip Material. This causes the tool to machine the opposite side of the blade. Click OK. Click Generate. Click OK to complete the operation. Click Edit Rules. In the Events Used section of the dialog box, double-click Orientation Mode equals Fixed to edit the event. Click Reverse Direction. This vector defines the fixed orientation of the head for polishing the opposite side of the blade. Click OK in the Robot Tool Orientation dialog box. Click OK in the User-Defined Events dialog box. Click Apply Rules. Now we'll observe the final robotic machine tool simulation. Click the Program object. Click Simulate Machine. Click Play. Both sides of the blade are polished with no collisions or singularities occurring. Click Close. This concludes the demonstration of how you can simulate robotic machines using NX-generated milling toolpaths. Thank you.